For over 2 centuries, one island nation has defied the laws of geography. From a swampy colonial outpost to a global titan of infrastructure, Singapore's story isn't just about history. It is a masterclass in civil engineering. Where there was no land, they reclaimed it. Where there was no water, they captured it. From the 19th century iron of Cavenagh Bridge to the AI-driven digital twins of 2025. This is the evolution of a city built by design. This is Singapore, expanding the impossible. In 1822, Singapore's engineering journey began not with a grand structure, but with the fundamental reshaping of its topography. To transform a swampy riverbank into a viable commercial port, early engineers executed the Boat Quay Earthworks. This was the precursor to modern land reclamation. Workers leveled a small hill at what is now Raffles Place, using the excavated earth, over 40,000 cubic yards of it, to fill the marshy southern bank of the Singapore River. From a geotechnical perspective, this was a massive undertaking for the era. The challenge was stabilizing the soft marine clay to support the weight of warehouses and wharves. This crescent-shaped quay became the economic heart of the colony, proving that Singapore's growth would always be a battle against the constraints of its natural geography. It set the precedent for a city that would literally be built on borrowed earth. Completed in 1869, Cavenagh Bridge remains a masterclass in 19th century Victorian engineering. As the oldest bridge across the Singapore River, it serves as a testament to the era of cast iron construction. The bridge was manufactured in Glasgow by P&W McClellan and shipped in segments to Singapore, a logistics feat of the industrial age. Structurally, it is a suspension bridge, but with a rigid iron frame that differs from the cable-stayed designs we see today. Engineers had to calculate the load-bearing capacity for horse-drawn carriages of the time, though it was eventually restricted to pedestrians as the city's weight grew. Even today, the bridge's steel and iron integrity remains intact, a silent witness to the shift from manual labor to precision-manufactured infrastructure. By 1923, Singapore's connectivity reached a new scale with the Johor-Singapore Causeway. This 1,056-meter-long structure was one of the largest engineering projects in the Far East at the time. It wasn't just a road, it was a massive rubble-mound causeway. Over 2 million cubic yards of granite were quarried from Pulau Ubin and Bukit Timah to create the foundation. Engineers faced the daunting task of managing the hydraulic pressures of the Johor Strait. Because the causeway blocked the natural flow of tides, it effectively created 2 separate tidal compartments. The solution was the inclusion of a lock system at the Johor end to allow vessels to pass, featuring a 570-ton rolling lift bridge, a marvel of mechanical engineering that moved with enough precision to handle both rail and road traffic. In 1961, Singapore launched its most audacious engineering gamble, the transformation of the Jurong mangrove swamps. Led by Dr. Goh Keng Swee and Dutch engineer Albert Winsemius, this project involved shifting mountains to fill the sea. Entire hills were leveled to provide the millions of cubic meters of fill required to stabilize the crocodile-infested marshes. The engineering focus here was on industrial scale. They didn't just build factories, they engineered a self-contained ecosystem with deep water berths for shipping and heavy-duty infrastructure for manufacturing. This was the birth of plug-and-play industrial land, where the topography was bent to the will of economic necessity, turning a lost region into the engine of Singapore's GDP. When Changi Airport's first terminal opened in 1981, it represented a triumph over one of the most difficult soil profiles in the world, Singapore marine clay. Reclaiming 870 hectares from the sea was the easy part. Ensuring it didn't sink was the engineering challenge. To manage the soft, compressible clay, engineers utilized prefabricated vertical drains, PVD, and massive surcharging. Over 140 million linear meters of drains were installed to accelerate the consolidation of the soil, squeezing out water that would normally take decades to dissipate in just a few months. This process increased the undrained shear strength of the soil, providing a stable foundation for the runways that would eventually host the world's heaviest aircraft. The launch of the Mass Rapid Transit, MRT, in 1987 marked Singapore's descent into the subterranean. The central challenge was tunneling through a geological jigsaw puzzle of soft clay, loose sand, and hard granite. Engineers employed massive tunnel boring machines, TBMs, that had to operate beneath a densely populated city without causing surface subsidence. In many areas, they used the earth pressure balance method, where the pressure at the TBM cutter head is carefully managed to match the surrounding soil pressure. This precision engineering allowed for the construction of 15 underground stations and 22 kilometers of bored tunnels, laying the foundation for a rail network that today serves millions. The Marina Barrage is a 3-in-1 engineering marvel completed in 2008. It serves as a freshwater reservoir, a flood control system, and a lifestyle hub. The core engineering feat lies in its 930-meter-wide steel crest gates. These hydraulically operated gates manage the water level of the marina basin with surgical precision. During heavy rain and low tide, the gates lower to release excess water into the sea. If the tide is high, 7 massive drainage pumps, each capable of moving an Olympic-sized swimming pool of water in 1 minute, kick in to discharge water. This transformed a saltwater estuary into a freshwater source, effectively increasing Singapore's water catchment area by 1/6. Marina Bay Sands is defined by the SkyPark, a 340-meter-long platform bridging 3 tapering towers. From an engineering perspective, the SkyPark is a miracle of balance and weight distribution. The towers themselves were built with a pre-camber. They were slightly tilted during construction, designed to settle into a perfectly vertical position once the weight of the SkyPark was added. The most iconic feature is the 66.5-meter cantilever, one of the longest in the world. To handle the dynamic loads of wind and the weight of the infinity pool, engineers used a sophisticated system of movement joints. These allow the 3 towers to move independently in the wind, while the SkyPark remains a stable, unified structure 200 meters in the air. In 2022, Singapore looked to its reservoirs to solve its land scarcity for solar power. The Tengeh floating solar farm is one of the world's largest inland floating solar systems, spanning 45 hectares. The engineering challenge was twofold: protecting the water quality and maximizing energy yield. The 122,000 solar panels are mounted on high-density polyethylene (HDPE) floats, designed to withstand the humidity and UV exposure of a tropical reservoir. The water provides a natural cooling effect, increasing the panel's efficiency by up to 15% compared to land-based systems. This project proves that even with limited space, Singapore can engineer a pathway toward 100% green waterworks. The Pulau Tekong Polder system, completed in 2025, marks a historic shift in how Singapore reclaims land. For the first time, Singapore did not use the traditional infill method. Instead, they adopted the Dutch Polder method, creating land below sea level. The engineering involves a 10-kilometer-long coastal dike that protects the low-lying land. A complex network of drains and pumping stations ensures that even during intense rainfall, the polder remains dry. This method reduced the amount of sand needed for reclamation by 50%, providing a scalable engineering solution for Singapore to defend against rising sea levels caused by climate change. From the first handful of earth moved at Boat Quay to the digital twins of today, Singapore's engineering evolution is a testament to what is possible when precision meets persistence. We've seen a nation literally rise from the sea, turning constraints into skyscrapers and swamps into global hubs. But this transformation is nothing compared to what's planned for 2050. The blueprint for the next century is already being drawn, and the impossible is just getting started.